everyone. The purpose of this video is to talk through the summary of the differences between the car lab and the ball lab. I'm going to start by talking about the forces and motion. I'll then discuss the displacement versus time graph differences and the velocity versus time graph differences. Notice that in the car lab, we did not actually create this graph. So we're kind of going back to the car lab and reviewing what that graph would have looked like. The rest of these graphs you have indeed created as we're working on the labs. All right, so let's start with forces and motion. So in the car lab, what did we see? We saw a car. This is exactly what a car looks like, of course. We saw a car moving at a constant speed. The velocity might have been, 15 meters per second, for example. So the car was moving at the same speed the entire time. What did we see in the ball lab? We saw the ball start at a velocity of 0 and then move faster as it fell. So the velocity just got faster and faster as the ball was falling until it hit the ground. And so the velocity here was, let's just say, for example, 2 meters per second, then maybe it went up to, 6 meters per second. You should obviously use your table and your information to come up with reasonable numbers, but we see the velocity was changing. We started with the velocity of 0 when we were just holding the ball, and then it fell continuously faster until it hit the ground. Let's see what that looks like in terms of forces. So, what forces were acting on the car? Hopefully you're telling yourself gravity. We're here on Earth, so we have gravity. The car was on a road. The road was supporting the car. That means we also have normal forces. We also had a force from the car moving forward and a force of dynamic friction. I see that these forces are balanced. Another way to look at this is that F net, if we add up all the forces, they will be 0. The y direction forces, F normal minus F of gravity is 0. These are exactly the same length. And the same is true in the x direction, that we have F of the car minus F of dynamic friction also equal to 0. Our forces are balanced, they equal 0. This means we saw constant motion. Another way to say that, no acceleration. The car was just moving along at the same exact speed. All right, how about the ball? What forces were acting on the ball? Well, on the ball, we had F of gravity. So if we look at F net, the forces in the x direction, left and right, or the x direction, well, I see there's no force in the x direction, there's no force in the y direction, and so in the f direction, we actually do have balanced forces. We have velocity equals 0 in the x direction, or right and left. However, if I look up and down, I see I have F of gravity, the force of gravity, minus nothing is just going to be the force of gravity. And so all of a sudden, I have an unbalanced force, whatever amount that force of gravity is, I have an unbalanced force, which means I have accelerated motion, not constant. So conceptually, we should understand balanced forces give us constant motion, meaning an acceleration of 0. Unbalanced forces give us accelerated motion, or mean that the velocity is changing. Velocity is a different amount as we continue moving. It's not constant, and that comes from having unbalanced forces, either in the right and left direction, or the up and down direction, or both. In this case, just in the up and down direction. But if it's unbalanced in one situation, we consider it unbalanced. Okay. So the next thing we're going to talk about, we've talked about FBDs. We're now going to talk about displacement versus time graphs. So in the car lab, so displacement time graphs, remember S for displacement from that Latin word, spatium. So in the car lab, when we graphed S versus T, we also graphed S versus T in the ball lab. What did we get in the car lab? We got something that looked kind of like this, a nice straight line. In the ball lab, we got something that looked more like this. So the displacement time graph was linear for the car lab. The displacement time graph was quadratic in the ball lab. Okay, how should I interpret this? Well, there's a few things we can consider. I can look at, for every amount of time, let's say this is 1 second, 2 seconds, 3 seconds, 4 seconds, for every amount of time, my car traveled exactly the same amount. So let me show it this way actually. So at s equals 1, the car had gone this distance that I had agreed. At s equals 2, the car moved exactly the same amount as it did in the first second. At s equals 3, the car moves again exactly the same amount of distance as it did in the second second. That means the velocity is not changing. We move the same displacement for every second that passes. The other thing I notice is that the slope of the line is constant. So my slope, which corresponds of course to velocity, whatever my slope is here, let's say, I don't know, my velocity equals 4 meters per second. Well, I have the same slope here and here and here and here. On a linear line, my slope does not change. All right, let's take a look at ball lab. I'm gonna again think of this in terms of different time intervals. In ball lab, we are talking more about 0.1 second, 0.2 seconds, 0.3 seconds. So in 0.1 seconds, this is how much the ball was displaced, just a little bit. In the second time interval, well, my ball actually moved further. This difference in the amount it moved is bigger. In my third time interval, notice the ball moves even further. And so what does that mean? It means the velocity is changing. It means we move more, sorry, my move and more look very similar, more displacement for every second that passes. And let's think about the slope of that line, the slope of that line. Well, the slope at this point right here, if I draw a tangent line to get the slope at this point right here, whatever slope this is, let's say it's, I don't know, 2 meters per second, that's going to be a different slope at a different point in the line. Maybe here, the slope is, I don't know, 5 meters per second. For example, these numbers are just an example. So what am I seeing? I'm seeing the slope changes throughout the line. Remember, in both of these instances, the slope is actually the velocity. So I have different slopes along every point of this line. If I were to draw in my tangent lines, my slope is changing at every point in this line. Okay. So we've now done FBDs, we've now done ST. We're now going to look at velocity and time graphs. So just as a reminder, in both of these cases, we had our ST, we had a straight line here, and then here we had, let's make these lines nice and straight, ST, and we had a quadratic here. All right, we then drew a graph with the velocity and the time. Well, excuse me, that should be velocity and the time. Okay, so at this time interval, how would I get the velocity? Well, my velocity would be whatever the slope is. Let's say my slope is equal to 10 meters per second for this graph. So for every amount of time, we're going to get the slope. So at my time equals 1, my slope is 10 meters per second. At my time equals 2, my slope is still 10 meters per second. Sorry about that. At time equals 3, my slope is still 10 meters per second, etc., etc. At every time point, my slope never changes. My slope is not changing. Remember, slope is velocity, slope from my ST graph, I should say. Velocity is not changing. This is constant motion. In the ball lab, what do I see? Well, I see that at this point, I can get a slope by doing what's called taking the tangent line. I figure out what is the slope of the line at this very point. So whatever slope this tangent line has, let's say it's 1 meter per second. Well, at time 1, I'm going to plot 1 meter per second. At my next time interval, I'm going to take another tangent line and I'm going to figure out the slope. Maybe the slope is 2 meters per second. So at that second time interval, 2 meters per second. My third time interval, my slope, maybe now it's 3 meters per second. So on my time plot, I would plot 3 meters per second for my slope, or better yet, my velocity. And then I'm going to end up with a line that looks something like this. All right, so thinking about my VT graphs, my velocity time graphs, my final step here would be to analyze the slope of my velocity time graph. So here I see the slope of this graph is 0. My units, well, velocity is a units meters per second, time is a unit seconds. So my slope unit would be meters per second, or meters per second squared. And so I'm seeing that I have 0 meters per second squared, and that is actually the acceleration. The acceleration tells me how does the velocity change over time. No change in velocity over time, which means there's no change in acceleration. Over here, well, my slope here, again, same units, is going to be some amount. Maybe if I went with these numbers, my slope would be 1 meter per second squared. And so in the velocity time graph, my slope is actually the acceleration. So I see that my velocity changes at each time point. I have a different velocity. I'm moving faster and faster and faster and faster, which means I have some amount of acceleration. I am moving at faster velocities over time, which means I do indeed have acceleration. And I can find the exact acceleration from the slope on the velocity time graph. Your slope is likely not 1. You should have gotten a different number. These numbers, again, are just examples. All right. Reach out to your teacher as you have questions. Thanks for watching. This is one of those concepts that you just have to go over in your head again and again until it starts making sense. Get that repetition you need, get that practice you need, and we're here to help and support however we can. Have a good day.